Quantum computing is naturally hybrid. You have quantum and classical computers having to work with a very high speed on par with each other. So that makes this classical component extremely important. And, part of really understanding what the quantum computer actually looks like when it operates is really understanding the classical control and electronics.
People are implementing error correcting codes which are going to have a very large classical computing component to it in the decoding and in the kind of fast feedback of the error correcting codes. And bringing in a hybrid approach where we have really, really powerful and purpose-built classical computing into those systems is going to be a really important part of that.
I think we're going to see the state of quantum simulation advancing to the point where we are really going to be comfortable saying that we have finally achieved some kind of quantum advantage within that context.
For me, the big advancement is we have to make the hardware better and better. And, that's what I'm focusing on. And my idea is, how to build the hardware in a way where we can scale up to, say, millions of qubits, so we can build an error-corrected machine and just build a general-purpose quantum computer.
We're talking about sort of real-time interactions between quantum and classical, but even there's like an interesting space of what's possible, from sort of short computations that are really fast and very closely coupled to the quantum devices, to more powerful computations and things like decoders for error correction, towards things where you really have more traditional high-performance computing systems working side by side with quantum computers to sort of jointly solve a problem.
Error correction doesn't arise when you blast your signal with something. It arises when you measure, think, or the machine thinks, and decide, now what do I do? So it has to come up, get processed, and then go back down again.
You increase the classical complexity, you reduce, in a sense, the quantum complexity, and understanding this trade-off is the, I think, essence of moving this field forward.
When we start to combine different types of adaptivity and quantum classical combinations, right? Like when people start to look at how they combine error correction and mitigation all at once, right? How we embed error or retuning and calibrations into the circuits, how we look not only at the hybrid algorithms in the sense of having the quantum sequence and the classical computation, but looking at, the scheduling across the different computational platforms as well.
Quantum computers have a relatively slow clock rate compared to classical computers. So it would be much more efficient if you had a distributed quantum computing system where you can call various QPUs and calculate different bond distances in each one of those QPUs. What started as just an idea, now it's becoming clearly a necessity. Basically, quantum computers cannot be useful unless you have this level of parallelization of quantum computations.